Okay, so hello everyone. First of all, thanks for having me. It's a pleasure to be speaking at QNLP again. And today I'll be presenting quantum data representations for audio natural language processing, although we'll see that the audio world could be replaced with signals in a more general sense. But yeah, let's start and see. So I am actually pursuing a PhD in quantum computation at Politecnico di Milano, and what I do in my PhD is searching for quantum data representations. So I work with fault-tolerant quantum computers, meaning that I don't generally do experiments. I work for far-term quantum algorithms, and I try to quantize data representation algorithms and bound the runtimes of those algorithms, meaning that I don't usually deal with VQE or QAOA, but with other routines in the gate model. So this field is very close to quantum machine learning, and it's actually it's maybe a subfield of quantum machine learning, and I would like to stress the importance of finding data representations. That's because even though, say, in one day we won't be able to gain exponential speedups for quantum machine learning, if we get polynomial speedups for data representations, that is still interesting. Because maybe we don't get speedups in the computation of the machine learning algorithms, but if we allow to transform our data in new feature space, and we can do this with a polynomial advantage, meaning that we can afford some new transformations that we couldn't afford classically, we might allow simpler models to learn better stuff. So we might improve the accuracy of our models. And in particular, today I'll be talking about two data representation algorithms. The first one I'll be presenting is an algorithm to find sparse representations. And the second one is, they are some SVD-based methods. So I already discussed some of them in QNLP 2020, but we have some updates. So let me convince you a bit about the importance of data representations again. Say that you have a data set. This is a simple data set, so it lives in one dimension. And this data set has two labels, a label 0 and a label 1. And if you picture this data set, it looks like that. And your model is a very simple model. You have a function, the function takes a point, and it outputs the label of the point, so either 0 or 1. But the model basically outputs the class by just comparing your data point with a threshold. So basically the question of whether this model can correctly label your data is, can I set a threshold in this line such that I correctly classify those points? But this is problematic because, of course, when you set the threshold somewhere, then you're gonna have that you cannot linearly separate those points. But then, what happens if you transform your data in a new feature space? So you just squared your data points. Now you have a parabola, and if you project those data points on the y-axis, you have something like that, and now your model can correctly shatter the points. Okay, so we kept the model simple, but we are dealing with data in a new feature space, and that's what it is about. Okay, so the first part of the talk is about an algorithm for learning sparse representation, and it's called the matching pulsed algorithm. We have the following problem. So we have a signal. That in this picture, we have a continuous signal, but you can imagine to have a discrete signal. So you sample it, and then you have a vector of a fixed dimension. And then you have a bunch of vectors, and you want to express your signal as a linear combination of this set of vectors. The fact is that you have more vectors than what is needed to span the space. So you have multiple solutions that approximate your signal or that reconstruct your signal, but you want to find the sparsest. So you want to find the sparsest linear combination of those vectors that approximate your signal. And there are cases when signals are sparse with respect to some set of vectors. For instance, this is a medical application. This is a ECG signal. And here you have the DCT basis. So this is actually a basis. It's not, it's not the problem of learning sparse representations yet. But you see that if you transform the ECG signal in the DCT basis, then you have a vector which has only a few non-zero components and a lot of zero components. And the whole family of vectors acts like that. So the whole family of ECG stuff is sparse with respect to this dictionary, to this set of vectors. This is nice because you can use these. If you can represent your signal as a linear combination of, a sparse combination of stuff, then you can use this sparse representation for several applications. So the first one, for instance, is data compression. And this is actually how JPEG works, for instance. So if we agree on the set of vectors that we want to use to represent our signal, then instead of communicating you the whole dense signal, I can just communicate the non-zero components. And you'll be able to reconstruct the original signal. So this is useful for signal coding, audio coding, or signal compression. This is also useful for signal reconstruction, denoising in painting, which can be used for audio too, because say white noise, so I add white noise to my signal, and basically this sparse representation is acting as a compression, but you cannot really compress white noise, meaning that in the sparse representation you will have a lot of little spikes. You threshold them off to 0, for instance, and you transform in your original domain, and you can perform denoising. Or there are a couple of nice papers from Terence Tao and other people about super resolution, and then you could actually reconstruct your signal in frequency, or you can see it as a kind of a Fourier transform. You could reconstruct your signal in frequency even if you don't have enough samples to reconstruct your signal. And then you can assume that different distributions of signals, so different families of signal, they are sparse with respect to different vectors of your dictionary. And basically, you can use the spectrum as additional features for your machine learning algorithms. Because if you have two families of signal that are sparse with respect to different vectors, then you can just compare the spectrum and find anomalies, for instance. This is, for instance, super nice in this example here. If you put a spike there, which is an anomaly by the sensor, you would see that the spectrum significantly changes. Okay, so in a more formal way, you have a vector, which lives, for simplicity, it's a vector of real numbers of length n, and then you have a set of vectors. The set of vectors I was speaking about, it's called dictionary, and those vectors are called atoms. You can assume them to be units, like of unit norm. When I mean unit in L2 norm. And you also have a reconstruction error, meaning that you want to reconstruct your signal, but your reconstruction is like in an epsilon ball from your original signal. And the problem is formally defined like that. So it's a constrained least square optimization, where the constraint is on the sparsity of your solution. So you're minimizing the L0 norm of your solution. Unfortunately, this problem is NP-complete. So if I want to find the optimal solution to this problem, then I'll need to waste a lot of time, a lot of computational time. But in practice, since this finding sparse representation has a lot of useful applications, there exists a number of greedy algorithms that can tackle this problem with suboptimal solution in polynomial time. When I mean polynomial in the number of atoms and in the signal length. And so there are a few greedy strategies. One of them is the matching pursuit algorithm, which is the one that I'm going to present soon. There is the orthogonal matching pursuit algorithm, which is very similar. And then there are a number of L1 relaxations of this problem. Like instead of minimizing the L0 norm, many people optimize the L1 norm. And in some specific case, you can obtain the optimal solution. And there are also a number of interesting related problems that are like about dictionary learning. So you're given a signal and you want to learn the dictionary for which your family of signal is sparse. And those family of, dictionary learning problems use those other algorithms as subroutines usually. Okay, cool. So this is the matching pursuit algorithm, which is the first one that I decided to tackle. And it works like that. So it iteratively updates the solution. And again, it is suboptimal. So what it does is it stores in memory a representation of the residual, which is the part of the signal that your solution hasn't approximated yet. Then you have your solution at the beginning is at 0 vector, and you iteratively update the solution. So at each iteration, you update the solution and the residual. The way you update the solution and the residual is in this place here. What you do is you take the inner product of all the atoms with your signal, with your residual, and you select the atom that produces the biggest inner product in absolute value, just this step here. Once you've found this atom, which is the best one at the current iteration, you can use it to update the solution and the residual. And then the stopping condition is either when your solution is not sparse enough, meaning that the algorithm is failing because it's greedy, again, or when the residual has a small norm. That's because you are already in this approximation area. So those are two stopping conditions. Now, the slow part of the matching pursuit is exactly this stage, which we call the sweep stage, because we are sweeping all the atoms to compute the inner products. And this exactly has complexity k and m, where, because you're computing m inner products of vectors of length n, hence why this term, and you're doing it k times, where k is the number of iterations. You can think of k as L, like the sparsity threshold, more or less. Even though the matching pursuit might update the same index of the solution multiple times. So k could be a little bit bigger than L, but it's O of L, let's say. In the orthogonal matching pursuit, they fix that and they only update one solution at a time, but you have to solve an additional least square problem over there. So the idea is to have a quantum algorithm that speeds up this sweep stage. And we do it in this way. So we only want to prepare quantum access to the dictionary and to the residual. Then we will store the solution classically and update the solution classically. So in the end, we will have a classical representation of the solution. Then we want to compute the inner products between all the atoms and the residual in superposition. And the strategy is to use basically Grover search on steroids to find the maximum absolute value to get a polynomial speedup. Okay, so I'll take again some concepts that Alessandro presented this morning and introduce them again. So to prepare quantum access to the dictionary and the residual, we assume the existence of a QRAM, which is basically a device that works like that. So you have a place where you can store your classical data. And of course, like those are memory cells and they have an address. What you want to have is a circuit such that you have two registers, you input the address in the first one, and it gives you the binary encoding of what you wrote in the memory cell in the second register. And you want this unitary to act in superposition on all the possible addresses. So that's the assumption of a QRAM. And as Ale was saying, there are a couple of proposals for such QRAM. The first one was from Giovannetti, like the bucket brigade one. And recently, Han had some nice results on the error resilience of the QRAM. So that's the only strong assumption that we make. So if you have a QRAM, what you need to do is, say you have a residual. So you have the residual at the beginning. you want to create this kind of access, which is you have a zero state, sorry, and your unitary needs to create an amplitude encoding of your residual. The way you do that is you build this structure here, this tree, which is called a KP tree. You can find some references in here. And you need to store the entries of this tree in a QRAM. If you store the entries of the tree in a QRAM, then there is a procedure that performs this mapping or that mapping over there in logarithmic time. So if you have a vector of length n, in log n, you can create that state. So that's the input. So we will have our representation of the residual will be stored in this KP tree in RAM. So when we update the residual, if we have to update the whole residual, we will have to pay the time of updating the whole tree, which is n log n. Using the same kind of tree, you can also build quantum access to the dictionary. And building quantum access to the dictionary means having a unitary such that you query a column. So you query an atom, and it gives you an atom here, where the atom is amplitude encoded. And basically, by combining, again, those trees in QRAM, you can build such a quantum access. And the time it's just, the query time is logarithmic. The storing time is linear in the size of the dictionary, more or less. It's a little bit super linear. But you only need to store the dictionary once, and it's read-only. Like, you store it, and then you have this, that the dictionary will work for a whole family of signals, and you don't need to update it anymore. So, okay, we created quantum access to the residual in the dictionary. Now, giving access to those two unitaries, we can use a procedure that, again, Alessandro presented this morning for distance estimation. It's a procedure that was presented also in the Q-means paper. Again, basically, Hadamard tests on steroids and in superpositions. And from these two quantum accesses, you can create this quantum state here, which is a uniform superposition that has two registers. One of the two registers is the index of the atom. So that here you are indexing all the atoms. And here you have the binary encoding of the inner products, between the residual and the atom. And you can build this superposition, which is a uniform superposition. And the procedure is quite fast, like it's by logarithmic time to query those states, some term that depend on the probability of failure, and you are linear in the error of this encoding here. Once you create this state, you can use this other routine, which again, it's basically using Grover multiple times with different oracles. So you use Grover a number of times, but you always change the oracle that you use to perform Grover. And you can find the maximum absolute value of this state in time, which is square root of m, which is square root of the superposition. And yeah. So in the end, if you chain together those routines, you get this kind of runtime here. So instead of KNM, you have this term here, which is given by the update of the residual, because you might have to update the residual in QRAM at each iteration, plus k times the search for the inner products and the time to create the inner products. So usually, this is the leading term, but of course, you have a dependency on the error as well, so you need to be careful, on how much error your application can tolerate, and this will depend on the dictionary too. Visually, the speed up is something like that. So these are rough estimation. You can find more experiments in the paper itself. So we are working on other algorithms that are based on the matching pursuit one. Another one that we are working on with Stefano Veneri and Stefano Zanero, who's my advisor, is a version of the matching pursuit where the input state is not a classical vector, but you have a procedure that generates this input state S. So you won't have the residual stored in QRAM, but you need to do everything with circuits. and you have that the dictionary is block encoded. And then we're working on other versions, which are a version of the orthogonal matching pursuit. There are a number of algorithms that could be interesting to investigate, like adding constraint to the orthogonal matching pursuit you can resolve in painting problems, like audio declipping problems. Or, yeah, also L1 relaxations are interesting to check. And again, same for KSVD and mod. Those are dictionary learning methods that are based on the subroutines that we are building. Now we go on the second part, which is about the quantum SVD-based techniques and can be applied to natural language processing tasks. So instead of using here the concept of sparsity, we're using a similar concept, which is, the application of SVD in natural language processing are well known, and you have that many problems in machine learning, many data sets in machine learning are low rank. So if you look at the distribution of the singular values of your data set, it looks like that, like they decrease exponentially. And in natural language processing, if you build a matrix like that, which is a bag of words, basically, so you have the documents on your rows and the terms on your columns, you just put the frequency of the word for the document in each cell, and you take the singular value decomposition of this matrix. You see something like that. Like this is actually taken from a data set, which is like a set of titles of conferences. You produce the bag of words, you take the SVD, that's what you get. And you can exploit this kind of sparsity to learn things about your corpus. Let me define something which might be also important. Like, of course, you know that the singular value decomposition acts like that, so you will decompose your matrix in an orthogonal matrix, a diagonal matrix, and another orthogonal matrix. And you have that the singular values are the ones that are being plotted here. You also have these terms that I will call factor score ratios. They are basically the square of your singular values under the square Frobenius norm of your singular values. They give a measure of the importance of the singular values. And we will be using them soon. So in QNLP 2020, I presented some quantum SVD-based techniques to build the models of principal component analysis, latent semantic analysis, and correspondence analysis. And I presented those three case studies. But today I'm going to present some other algorithms and extensions that you can use, and then I'll show you one example of how you could use those subroutines to apply those subroutines to QNLP. So again, the toolbox that we are going to use is similar to the one that we used before and to the one that Ale presented. So we have that data will be stored in a QRAM, and we have the same access model. Then we only need a few operations, so we need to be able to do quantum arithmetic operations and singular value estimation, which is a routine like that. I'll go back to that soon. Amplitude estimation and amplification, and then you need to do tomography on the states because you want to reconstruct the vectors. So basically, the core of this, using those routines, using this toolbox, you can build a framework that helps you retrieving a lot of information on the left singular vectors, the right singular vectors, the singular values, the factor score, and all those infos here. And everything is based on a simple idea, which is this singular value estimation one. So you are given a vector that you can write as a linear combination of the right singular vector of your matrix. And basically, you have a unitary that maps in another state the singular values that correspond to those singular vectors. If you apply this routine to the state of the matrix itself, you can create this state here, where you have that the singular values are written in their binary encoding, and the singular vectors are written in their amplitude encoding, actually. So performing the tomography on this state is a bit messy, but that's not what we need. The important stuff is that creating this state is quite fast, so it's linear in the approximation of the singular values, and you have this dependency on mu of A, which you can think of as a norm of A. It's like a Frobenius norm or something like that. There is a proper definition, of course. But the cool stuff is that if you have this state here, the state basically acts as a slot machine, where if you measure the third register, you get the ith singular value with probability which is proportional to the factor score ratio, so to the importance of the singular value itself. And so you're basically sampling the singular values from this distribution. So this is the distribution of the factor score ratios of the same data set that we saw before. So of course, the shape remains the same. And you basically sample the singular values according to their importance. On the simple intuition, last year, actually 2 years ago, we presented those kind of algorithms. So algorithms to extract the singular values, the factor score and the factor score ratios, some algorithms to extract the right singular vectors and the left singular vectors. And we bounded the runtimes of those algorithms. But let me go to the new algorithms that we designed after those ones. So the first of all is this one. So here the problem is you are given quantum access to the matrix A, and you know how much variance you want to retain, which basically means, the factor score ratios, if you sum them up, they sum up to 1. And you want to retain a piece of those, of those singular values there, and this is how much variance will be explained in your data representation. So you know where to set this threshold. This is an input of your algorithm. But you don't know what's the threshold for the singular value. So you know that you want to retain 30% of the variance, but you don't know which singular value allow you to gain the 30% of the variance. Then we have an algorithm that allow you to estimate this threshold theta that you will use to separate the singular values in this runtime here. And the idea is basically that what you can do is you set a threshold theta on the state that you saw before, and you do a controlled rotation on another ancillary qubit. You set it to 0 or to 1, depending on whether the singular values are bigger or lower than theta. Then you perform amplitude estimation, and you get a point in this other space. And you compare, like, if the point is near to the number, to the variance that you want to estimate, then you just stop. Otherwise, you do binary search. Then you have another algorithm that allow you to estimate the reduced rank. So say that now you know the threshold that splits the singular values. But you want to learn how many singular values are there. So say that this is like topic modeling, because singular values and singular vectors allow you to find the most relevant topic in a data set. But say that you want to count this number of topics, for instance. So the number of topics that explain the 30% of your variance. Then you can just use your threshold to perform a Grover counting algorithm, and you will have this runtime here, which has, again, a polynomial speedup on its classical counterpart. And finally, we have another algorithm that, given quantum access to the matrix A and the top k singular vectors, builds a quantum state which is the projection of your matrix A onto those singular vectors in this time here, which is quite fast. Like, it's just linear in the Frobenius norm of V, which is bounded by square root of k, and where k, you can think of k as the number of topics, for instance, so the number of singular values that you retained. And then the square root of p, usually you want to retain a variance which is 30%, 50%, 15%, but basically this is a constant. You can think of it as a constant. It's rare that it's approaching 0. So with this tool set, you could think of some experiments like that. I present you a toy example that you can use. A toy example for those routines. So I had a data set with some news, and I took 40,000 short description of those news, roughly 10,000 words and over 31 categories of news. And that's the plot of the singular values, again, so you see they decrease exponentially, even in this setting. The idea now is we learn how many singular values are relevant, so how many of them are enough. You just extract the top k right singular vectors. This was done classically. And then what you do is, for each document, you project it onto the, each right singular vector identifies a topic. For each document, you project it onto your topic, and you see how much of the norm is preserved. You take the top 5 documents with the maximum norm, and you plot them. So you just see them, see what topics there are. And if you do that, the first topics yields a lot of yikes and ouch. That's because, probably I should have applied more preprocessing to the data set, but it's still interesting. It still performs like a kind of data analysis. Like I could, after this, I could know that I should have preprocessed the data more. Topic 1, for instance, seems to be things that are being reported by people. Like, I felt like I shouldn't have said what I said, the senator said, and here said is a bit leading the topic. So the topic is about stuff that has been reported by other people. That's what it seems to me. Then there is another topic which is about Trumps and politics, apparently. And I thought that it was interesting, but till now I had the doubt that this model was basically overfitting on some words, like Trump, and said in the previous the previous slide. Then there was this 10th topic, which was a bit more interesting, which was basically connecting women and rights. So it's not only about women. You can see the word women in every sentence, but I couldn't find a word that talks about rights that is always repeated in those news. But, you could definitely see the stuff, the flow. And so with our quantum model, what we can do is, when we have our data and we extracted our singular vectors, we build quantum access to those singular vectors, and we project our matrix onto the singular vector that represents the topic. So now we obtain a matrix from where you can sample each sentence by its importance for the topic. So you just sample the state, you get the index, you go check your data set and plot the sentence and have a look at those topics. And so that's okay. So that's something you can do. And you can do that quite fast because mu of v, if v is only one topic, it's equal to 1. And if you check like the square root of the ith factor score ratio, if you check the 50th one, it's 25, which is okay. Like 1 over 25, it's quite doable and fast. Okay, and you can do that, of course, for the several topics. So say you have your singular vectors, then you can fastly perform the mappings on your quantum computer. As a last thing, I would like to say that, again, we saw that all of our runtimes depended on errors and probability of failures. And when we designed the algorithms, they weren't thought specifically for NLP. They were thought as routines that you could use in several places and frameworks. Like, it's basically a framework for SVD-based data representation. You can use it for multiple applications. Now, the problem is we actually need to enable data scientists. Like, I'm Politecnico di Milano, and my university is full of engineers. There are no proper courses on quantum computing yet, but there are a lot of engineers that are able to do data science. And if we gave them access to those routines, they could understand. They could find nice applications of those algorithms and study for which kind of applications those are useful. And that is why, like Ale presented at the end of his talk, we developed this framework where you can basically analyze the runtime parameters for a specific data set. So you take a data set, you have our runtimes, and you can estimate those error accuracy parameters and probability of failures for your specific data set. And we basically forked scikit-learn, so it's easy to use for data scientists. And we are having students trying that to find application of quantum computers, where quantum computers could have the practical advantages. Because then you estimate the parameters and you get an idea of how many features and how many samples you need for the problems to be efficiently solvable with quantum computers. And if you discover that in your application the number of features is not reasonable, then maybe it's a good area. And that's the end of the talk. So if you have questions, I'll be pleased to answer them.